Universal Serial Interface, or USI in short. It is not a protocol, but an interface for serial communication that can mimic a variety of standard protocols. What are we going to do in this chapter? First, let's talk about one wire once again, but this time we will examine the similarities of one wire and UART. In the second part of this lecture, USI is introduced. In the last chapter, we discussed the search ROM algorithm in greater detail. It is used by the one-wire master to find all slaves connected to the one-wire bus iteratively. As noted before, if the master manipulates the wire, it is indicated in blue in the waveform. As an example, this reset pulse is generated by the master to align all slaves and bring the communication interfaces to a known state. On the other hand, if one or multiple slaves manipulate the value on the wire, it is marked in red. This presence pulse, indicating to the master that there are indeed one or multiple slaves present on the bus, is an example for slaves accessing the wire. We had UART some time ago, and as a reminder, here is the entire frame in waveform. We have the start bit, which toggles an idling line in a high state to a logical 0. After that, the data transfer starts. At least 5 bits are transferred. However, the UART protocol is universal, as the name suggests, so the frame can be configured to carry up to 9 bits. After the data, an optional parity is inserted, which then is followed by 1 or 2 stop bits, which are always high. Here we see what happens if the master of the one-wire bus would like to transmit a 0 or 1 to the bus. First, it pulls down the wire and, depending on the value to be transmitted, either lets it go so that the wire recharges, or holds it in a low state for the entire bit transfer of 60 microseconds. Around the 15 microseconds mark, the slaves sample the value of the wire. It is possible to get the same waveform in UART. The line idles high and the start bit is always 0, which is very similar to the beginning of the bit transmission in one wire. The only issue that we have to consider is that, in contrast to one wire, whose master lets the wire recharge at the end of the bit transmission, in UART we still have the stop bit to transfer right here. The question is that, apart from the number of stop bits mentioned earlier, in UART we can configure the transfer rate, the parity, and the data bits. So what shall we use to come as close as possible to the bit transmission in one wire? First, the transfer rate. Let's say we transfer 8 data bits. That means, including the start bit, all 9 bits, that is the start bit, and the 8 data bits, need to be transferred within 60 microseconds. The stop bit is high, so this is outside of the one-wire frame. Therefore, if 9 bits are to be transferred in 60 microseconds, each bit in UART needs to take 6.67 microseconds. That means, in 1 second, 150,000 bits are transferred, resulting in a transfer rate of 150 kilobaud. That is, if the UART is configured with 8 data bits, no parity, and 1 stop bit. And it changes if the UART is, for instance, configured to send 9 data bits per frame. Therefore, if the UART TX part mimics a one-wire master, and this master would like to transmit a 0, it sets the UDR0, which is the UART data register, to 0, so that 8 zeros are transmitted until 60 microseconds passed. If it is a 1, the data register needs to be all 1s, since the start bit is always 0. The difference between UART and one-wire master is that the one-wire master lets go of the wire while the UART TX actively drives the wire. The reverse, that is, the one-wire slave replies to the master, is slightly different. Again, the UART TX transmits all 1s as shown here. Let's see what the receiving RX line reads. First, this is the start bit, so this one is ignored and will not be stored in the data buffer. It is just here for completeness. If there is no slave pulling down the wire to its logical 0, the data buffer just reads 1s, since the bus idles high. In fact, it is driven high by the TX interface. If the slave replies with 0, it actively pulls down the wire as shown here in red. Despite the fact that the TX module keeps writing a 1 to the bus, the RX interface keeps reading 8 zeros. Remember that this is the start and this is the stop bit, and they are not part of the data transfer and therefore not stored in the UDR0. That means if the first or second most significant bit, or probably both, in the RX buffer are 0, then the slave wrote a 0 to the bus, a 1 otherwise. As you can see, the data buffer for the TX interface is different from the data buffer of the RX interface, although both of them are called UDR0. The reason is that despite they carry the same designation, both buffers are different. This is the UDR0 for TX and this is the UDR0 for RX. The TX and RX module are separate entities, and in the UART chapter we even discussed that you do not have to activate both of them at the same time if you do not want to. Then, in one wire, we have the presence and the reset pulse. However, the reset pulse is a lot longer than 60 microseconds that we have the UART frame configured to be in. If the UART is to mimic that reset pulse, including accommodate the presence pulse, the TX line has to stay low for at least 480 microseconds initially. After that, the wire can recharge, hence we write a 1 to the bus from here onward. Staying with the 8 data bits, what is the duration of 1 bit, and can we slow down the UART that much? This is the start bit and this is the stop bit, so those do not contribute to the data transfer. Somewhere in between are our 8 data bits. Since the reset pulse is longer than the presence pulse, I assign 5 data bits to the reset pulse and 3 data bits to the presence pulse. That means if we can make each bit 100 microseconds long, so let's call it TB is 100 microseconds, the entire presence pulse will take 500 microseconds. That is well within the definition. Then the wire recharges, and now we do not care anymore what is happening on the TX side, since the master completed its task of sending the reset pulse. A bit length of 100 microseconds means that the transfer rate is 10,000 bits per second, or 10 kilobaud. That means we have to switch between two transfer rates depending on where we are in the one-wire protocol. A shift in transfer rate essentially means that the appropriate configuration registers, that is UBBR, needs to be modified. That is not really a problem and can be done within one CPU clock cycle. What do we receive on the RX side? If there is a slave present, we see first the reset pulse, since TX is somehow connected to RX. Then TX lets the wire go and it recharges. Depending on when the slaves react and transmit their presence pulse, we might see a 1 in the RX data buffer. If they react within 15 microseconds, this spike here might be too narrow to be recognized. However, the lower bits in the RX buffer should read 0 if slaves are present. If there is no slave present, then those bits will read as 1 and RX will be the same as TX. Somehow the TX needs to be connected to RX and the one-wire bus. Hence this setting might be considered. We have the TX here directly connected to RX. We also have a one-wire slave here that can connect the wire to the ground to write a 0 to it. However, that setting might cause an issue. In many situations, shown on the previous slides, TX transmits a 1, but the slave wants to write a 0 to the wire, hence this switch is closed. RX will read a 0 because no pin is strong enough to have voltage on the wire if it is connected to the ground. You might already guess what the problem is. Imagine TX wants to continue to write a 1. It has no idea that the slave pulls the line down to 0. Hence, the TX module connects this pin to VCC to write the logic 1. So the current goes from VCC through the microcontroller, comes out at the TX pin and goes directly into the ground. Hence, we have a short circuit generating not only unnecessary heat and a high power consumption, but it might also damage the TX pin. Therefore, we have to make sure that if this part is 0 and this part is 1, that no current flows from the pin to the wire into that direction. We do that by inserting a diode between the TX pin and the bus. In this case, the current cannot flow from the left, that is the TX pin, to the one-wire bus. However, if we want to write a 0 to the bus, the charge on the wire can be discharged through this diode and the TX pin into the ground. Since nobody can charge the wire to a logic 1 anymore by now, since the diode forbids the flow of current from the TX pin to the wire to even charge it to the idling one, we need a pull-up on the wire, otherwise its value will remain logical 0 all the time. This is an example how UART can be misused to mimic a behavior that falls into the specifications of the one-wire protocol. In the previous session we saw that protocols can mimic other protocols. As we know, the ATmega328P does not have a one-wire interface. Therefore, its UART can be used for the one-wire purpose. Another observation is that the ATmega328P, despite its small size, has 28 pins, and especially dedicated pins for communication. For instance, in many scenarios, a sensor is read using the I2C or TWI interface here, and the resulting data is to be stored or transmitted using the UART or SPI interface. That is not a problem, since the pins for both transmission protocols are mutually exclusive and there is no overlap. That means the sensor can be read and the data transmitted at the same time. The little brother of the ATmega328P is the ATtiny. It has the same CPU and computational is as powerful as the ATmega328P. However, as you can see, the number of pins were cut down. In addition, its program memory and its periphery was a little bit downsized. What is shown here is the largest of the little brothers, the ATtiny 85, with 8 KB of program memory and 512 bytes of RAM, which is enough for many projects. In fact, I do not believe that any of the exercises in this course so far would have crossed that line. Besides the ATtiny 85, there's also the ATtiny 45 and the ATtiny 25 with 4 and 2 KB of program memory together with 256 and 128 bytes of SRAM respectively. The pinout of all ATtiny models are the same, so it does not matter which I introduce here. As usual, for more information, I'm attaching the datasheet for the ATtiny to the resources folder of this lecture. The pinout of the ATtiny is a little bit cramped. We have the pin change interrupts for all pins except VCC and the ground. Then we have the waveform generators of the timers, albeit only 2 timers are available here. And we do not have port C and port D, but only 6 pins of port B. As you can see, here is I2C, SPI, and something called DO, DI, and USCK. These pins are shared among all the communication protocols. In the ATmega328P, data can be read and written to the periphery using all communication interfaces in parallel. So SPI can send data to I2C as well as UART, and both start to transmit the data while the SPI interface acquires the next dataset. That is not possible in the ATtiny. Here, the modules cannot work in parallel, and either the UART or the SPI or the I2C interface can be active since they share the same pins. That means at least two of those modules are just sitting there consuming power. So why not having a look at the supported protocols and see if there are similarities so that we can club those three distinct hardware modules together into one, like what we did with the UART and the one-wire protocol. Here are all three protocols, the UART in red, I2C in green, and SPI in blue at the bottom. First observation is that all communication wires could idle high. An exception is SPI. There, it does not matter what MUSI is as long as the SCK line is not clocked. The second observation is that most protocols have a wire dedicated to the clock. Even UART has it when the USART is considered. At one point in time, the data transfer starts. Interestingly, except SPI, all protocols start with a 0 on the data line. In I2C, we have the start condition, and in UART, the start bit. And the last important observation is that all protocols are serial and transmit the bits one by one through some kind of shifting the value in a register mechanism. The protocols differ in the structure. For instance, I2C is a bus, so it has an addressing mechanism among other specialties, while UART is a point-to-point connection. If the common denominator of all protocols is used and the specialties are shifted to software and hence become the responsibility of the developer, what will we get? This has been implemented in the ATtiny. So instead of two modules having nothing to do while one communicates, the common properties have been summarized into a single interface, the Universal Serial Interface, or USI in short. This is the block diagram for the USI. It looks a little bit confusing, but let's go through it step by step. Let's start with the USI-DR. The most significant bit of the 8-bit data stored here comes out of this wire, goes into this latch, and then, depending on the setting of this switch, is forwarded to DO, the digital output pin, or DI, the digital input pin. Let's ignore the latch for the time being and assume it is transparent. That means that this wire is directly connected like this without the latch. In case the output is different from the input for a protocol, the wire is connected to the digital out pin like this. This is the case for instance, SPI, in which MISO and MUSI are physically separated wires, or in UART, in which each pair communicates through a TX to RX pair. So the RX wire is never used to transmit data back to the original transmitter. The situation is different for I2C, in which we have an SDA line, which is used by the master as well as the slaves to transmit data. Since this wire is bidirectional, the outgoing wire will be connected to the digital input pin, like in this scenario. The digital in pin is pretty straightforward and connected to the least significant bit of the USI-DR. That means whenever the clock comes from here, the USI DR shifts the most significant bit out from here and the least significant bit in from here. I mentioned clock signal, so let's see what clock signals do I have here. This multiplexer allows me to choose the source of that clock signal. As we see here, either I have the clock coming from the USCK pin, like in this way, or its complement through this inverter. But I have more options. I can choose the clock signal to come from the compare unit of timer 0. That means whenever there is a compare match, the data register shifts. That is useful in case I have a protocol which does not have a clock, such as UART. I just have to set the timer such that there is a compare match for the desired baud rate, similar to what we did in the first part of this chapter. There we set the duration to 6.67 microseconds to mimic the one-wire protocol using the UART interface. So if the timer 0 compare unit triggers every 6.67 microseconds, a transfer rate of 150 kilobaud is achieved. Or as last source, I can choose UCI CLK of the control register UCR. Similarly, the multiplexer connected to a 4-bit counter. Essentially, this 4-bit counter counts the number of edges. That means after the USI DR shifted out 8 bits or shifted in 8 bits, this 4-bit counter overflows, since 16 clock edges were necessary to shift 8 bits. This overflow can be used to indicate that the transfer of 1 byte completed. For that, a clock edge detector is integrated between the multiplexer and the pin USCK. Otherwise, the clock signal to the 4-bit counter is the same as the one to the USI DR. We have not talked about this block. This 2-wire control block can detect start conditions in case the ATtiny functions as an I2C slave and can issue an interrupt if the start condition has been detected. For now, I will omit going through the meaning of all bits for the control and status register. They can configure the USI to be more adapted to the various protocols, and they become important if the developer has to implement a protocol. However, in this course, we have not yet reached the point in which we know how to even program the ATtiny. Hence, let's postpone that for the time being and concentrate on the overview. Important takeaway is that the USI gives some support, but many controls need to be implemented in software. Let's have a look at some examples. First, the SPI, which is one of the easiest. Literally, put data into the USI DR and start clocking it. Here, DO and DI are used to build one MOSI and MISO pair. Depending on the SPI mode, which there are 4, and which indicates at what clock edge the data is sampled and shifted, either the direct value of USCK is selected or the one through the inverter. Here, port XN indicates that the clocking of the SCK line is achieved in software by manually toggling the port B2 pin. Alternatively, the compare unit of timer 0 can be used for that purpose. A bit more complex is I2C. For one, the pin for data out and data in is the same. Again, the clock is controlled in software. First, a start condition needs to be created. In Atmega 328P, it was simply achieved by writing a few bits into the control register, and the Atmega generates a start condition automatically. Here, this is not the case. First, we have to make sure that the MSB of the USIDR is toggled to 0. Which is then followed by the toggle of SCL to 0. It is important to keep the order intact to not to violate the protocol specifications and to make sure that the I2C devices on the bus understand the protocol. As you can see, the developer has to manually drive the wires to create the start condition, as this particular condition is not in the common denominator and hence not included in the USI specifications. The same is valid for any other condition in the I2C bus, such as the stop or the repeated start condition. An exception is the 2-wire clock control unit, which is activated in the slave only. It detects the start condition and can generate an interrupt to, for instance, wake up the ATtiny from a powered down mode. So, what do we get by using USI? We have to write the control in software, but we do not have to bit bang the data line. So we get a bit banging with a bit of hardware support. While clocking is done manually, and for instance in UART the parity needs to be computed in software, the hardware automatically shifts the data register, so we do not have to take care of that. Also, we do not have to worry about the start detection in ATtinys acting as I2C slaves in the bus. In optimal cases and lightweight protocols such as SPI or UART, once everything is set up, we can just wait for the data being shifted out. The comparator of timer 0 can be used to create a clock signal, and then we can wait for the interrupt while the CPU can do other tasks. Interestingly, since the USI is so universal, it can be assigned entirely different tasks as well. For instance, the 4-bit counter here can be used as what it is, a timer clocked by various clock sources which can count to 15 at maximum. Or alternatively, since the comparator of timer 0 is connected to USI, this comparator can be set to the top value, that is the maximum value, and every time this maximum value occurs, this USI counter increments. Since timer 0 is an 8-bit counter in the ATtiny, this timer is essentially extended by another 4 bits, making a 12-bit counter available in hardware. Since the USI is equipped with an edge detector, this detector can be utilized to detect and issue an interrupt if an edge occurs. To achieve this, the counter is set to its maximum value of 15 and all bits are set. The next edge will create an overflow, which in turn creates an interrupt request. Or last but not least, the USI can be used to generate software interrupts. Imagine the counter is again set to its top value, that is 0xf in hexadecimal format. The clock source can be set to accept toggles from USI clock, that is the setting. This USI clock can be written to by software. Therefore, if the multiplexer is set to the clock source USI CLK and the developer writes a 1 to USI CLK, the timer overflows and again an interrupt request is issued. That concludes the chapter about USI. We did not go into the details of explaining the meanings of all the bits in the status and control registers of USI. It would not make sense as we do not know how to program an ATtiny yet, which will be the content of a chapter later in the course. But so far, what did we learn in this chapter? We saw that some protocols can be misused to mimic other protocols they are not designed for originally. And we talked about the Universal Serial Interface integrated into the ATtiny, which is a superset of functionalities for various serial protocols such as UART, I2C and SPI. Control and special cases for each of the protocols then needs to be implemented in software. Hence, USI is a bit like bit banging, but with some hardware support. And what will be next? The next chapter in this course will be about the analog digital converter. In the end, we live in an analog world which is unaware of discrete values that we have in the domain of computers. The converter is able to translate some of the analog values into digital ones so that we can work with them. And we will talk about the smaller analog comparator, which compares analog values. But more about that in the next chapter. See you in a bit, and thanks for watching.